Okay, guys. This lesson, right? This lesson was basically for grade 10, right? But what I understand is that these basics are very, very important to all of us, right? It's very important to all of us who is going to write a physical science paper, because this topic is one of the topics that a lot of learners say it is challenging, and I know why they say it is challenging. The only reason they say this topic is challenging is because they don't have these basics that I'm going to share with you, right? Am I audible?
Yes.
Okay, thank you. And then please tell me in time if maybe my network acts up, right? Okay. So here is the first slide. The first slide is electric circuit. This is for grade 10, but like I told you, these basics are very, very important to all of us, right? Because a lot of you think
Uh,
that, yeah,
so,
yes,
are you supposed to be sharing your screen?
yes, I'm not sharing. I think I am sharing.
No,
I'm not sharing.
I don't see anything on. I don't see anything on my side.
Okay, let me try again. No, I'm sharing. Let me stop and try to share again. Am I now sharing?
Yes, sir.
Okay, thank you. I saw the mistake that I did, right? I was screen recording instead of sharing, okay? Thank you very much, Mpone. Okay, so with
Yes, sir.
this, okay, so with this one, the lesson objective, what you need to understand after this lesson, right? After this lesson, by the end of this lesson, you should be able to explain why battery goes flat using energy transformation, right? And then understand the current is the same through each resistor in a circuit. Let me just up this. Sorry, sorry for that, right? Let me just answer. Hello? Okay, sure. Okay, sorry for that, huh? I don't know why it is ringing on the on this device also. Okay, but it's fine. Okay, you should be able to understand the circuit. Understand that current is the same through each resistor in a series circuit, and then describe the series circuit as potential different dividers. Calculate the total resistance in a circuit, and then understand the potential difference in is the same across resistors in a parallel circuit, and then describe parallel circuit as a current dividers, and then calculate the total resistance in a parallel circuit, right? So those things are fundamental. Those things you are supposed to understand them. After this lesson, you should be understanding them. So please make sure that you ask anything that you don't understand, right? Don't wait for me to go more slides, right? Just ask immediately when there is something that you don't understand. You have to ask, right? Okay. So here is the first slide where I'm just going to tell you this. This is just something that you should know, right? What about battery, right? About a battery. Why does a battery go flat? A battery goes flat because it runs out of chemical energy to provide electrical energy, right? Energy transformation in a circuit. A battery stores chemical energy. You know, a battery, if you break a battery open, right, you will find some material there. Some of you won't understand it. There's no need for me to explain them, right? You will find the material that is blackish in color, right? So that material are chemical, they are chemicals, right? So those chemicals, they've got the potential to change their form, like they've got chemical energy within them, right? They've got chemical energy within them. When they react, they give out electricity, right? So their chemical energy is transformed to electrical energy, right? So that is why the battery will be supplying electricity, is because the chemical energy within it is being transformed to form electrical energy. That is the transformation that you need to understand. The transformation within the battery. In the battery, there is chemical change. That is chemical energy is being changed to be electrical energy. That is very important, right? So that is what I need you to understand, the chemical reaction within the battery. What happens inside the battery? Chemical energy becomes electrical energy, right? Remember, energy cannot be created nor destroyed, right? It can only be transformed from one form to another, right? So in a battery stores chemical energy, and then when it is connected to a circuit or something, or a light bulb or anything, it will change that chemical energy to be electrical energy. And for an example, if the device that is connected to the battery is a light bulb, obviously the electrical energy will also be transformed to be what? To be light. If it's a heater, the electrical energy will also be transformed to be heat, right? So that is what you need to understand. Okay, over time the battery uses up all its stored chemical energy and the circuit stops working. This is when the battery goes flat, right? So that is very, very important to understand, right? That is very, very important to understand. Remember, I will share you these notes just for those big higher grades. It's very important just to understand this, right? Okay, and then we've got the key things about electric circuits, right? The key things about electric circuits is current, voltage and potential difference is one thing, right? So we've got current, voltage, and resistor. Those things you should understand what they are, right? So current is the flow of electric charges in a circuit, right? Current is the flow of electric charge in a circuit. It tells us how many charges pass through a point in a circuit every second, and the unit is amperes, and then the denotation there is going to be a capital letter I, right? And then the symbol is I. And then here is what you should think about current. If you think about current like this, it will be very, very easy for you to understand how current works, right? They're saying think of it like the flow of water in a pipe. More water means more current, right? More water means more current. So it means that if what do you call, think like this, let's think like the flow of water in a pipe. So if the water is flowing more rapidly, obviously there will be more water, right? So if the current is high, it means that there will also be high voltage, but I will understand this better once I give you this, right? Once I give you this. Okay, then current. So now let's go to potential different or voltage. Voltage, also called potential different, right? Voltage is the energy supplied to move charges through a circuit. It is the push that makes electric charge to move. Understand what is voltage? That is what voltage does. Voltage pushes current, right? Which means higher voltage, obviously higher current, right? Higher voltage, obviously higher current. So if they give you current, obviously you know that because current is high, it means it's because of high voltage, right? So those two things are directly proportional. Should also understand that current and voltage are directly proportional. Higher voltage, higher current. Lower voltage, lower current. Lower current, lower voltage. Lower voltage, lower current, right? They are directly proportional. So unit is volt, and then the symbol is V, and then think of it like water pressure. Higher pressure makes water flow faster, just like higher voltage makes current flow faster, right? So the current will be higher when the voltage is higher. Are we clear then?
Yes, sir.
Okay. So let's go to the next one. The next one will be resistor, right? Going on. What's going on now? Okay. The next one will be resistance, right? So the resistance is how much a material or device opposes the flow of electric current. It limits how much current can flow for a given voltage, right? And then we've got Ohm's law. We've got Ohm, right? The unit is Ohm, and then the symbol, we're going to use capital letter R, right? Think of it like a narrow pipe. It makes it harder for water current to flow, right? So like higher voltage, it means like if you are comparing it to water, it means that higher resistance, it will mean that the pipe is narrower, which means the water won't flow easily, right? Remember, the flow is what? The flow is current, right? So higher resistance, lower current, and we know that lower current means lower voltage, right? So voltage and current are directly proportional, but they are both inversely proportional to resistance. Are we clear there?
Yes.
Yes, because resistor does makes it difficult for current to flow, right? Resistance make it difficult for current to flow, right? So those are the basic things that you should understand, and then if you understand this, your circuits are going to be very easy, right? And I'm sure the reason that I made you all attend this, I know that this topic is considered one of the difficult topics by the students, right? Okay, so let's go to this one. Current in a circuit, in a series circuit. First of all, before this one, in fact, let me remove it, right? Before this one, I need you to understand this, the parallel and parallel. I need you to understand parallel connection vs series connection, right? So I need you to understand the difference between these two, right? So parallel, you know, parallel lines here is parallel, right? And then the series is like this, right? So you know parallel lines. Parallel lines, it means the other on top of the other, right? Or the other on the bottom of the other. So, and then series is the other in front of the other. So resistors with batteries, right? Batteries can also be connected in parallel like this, right? Here is the wire connecting the two. Here is the wire connecting the two, right? So these ones are the batteries connected in parallel. So here we've got batteries connected in series, right? So what is a battery? First of all, you need to understand what is a battery, right? A battery is the combination of many cells, right? So we call this one a cell. That thing that you go and buy when you want to put into a remote of a TV or decoder, right? That if you buy one thing, you didn't buy a battery. That is not a battery, that is a cell, right? But once you combine them, making them two, then you have got a battery, right? A battery is combination of cells, right? So in this case, a cell, this is a symbol for cell, right? This is a symbol for cell, which means that if we've got two, then we've got a battery, right? That is very important also to understand, know the difference between a cell and a battery, right? So let's say our cell here is 1,5 volts, right? One cell is 1,5 volts, right? So if you have got 1,5 here, 1,5 volts here, and 1,5 volts here, right? 1,5 volts here, and also here we've got 1,5 and then 1,5, right? So I'm starting to talk about them in a parallel connection, right? In a parallel connection and then in a series connection. So in the parallel connection, if you have to add the voltage of these two batteries, right? If you have to find the voltage of these two batteries, it's going to be 1,5 volts. The total voltage, or EMF, we call it EMF, right? The total voltage EMF is 1,5 volts, right? And then for these two, because we've got how many? We've got two here and they're both 1,5. For the ones in series, we add them. So EMF here is going to be 3 volts, right? So EMF there is going to be 3 volts. We add them when they are in series, and if they are in parallel, we don't add them, we keep them as they are, right? And in parallel, they won't, I won't explain this one, I'll just keep it as it is, right? But I'll just tell you, in parallel, you won't have a connection like this, right? This is parallel. Remember, you won't have 1,5 and 2 volts here. You won't have a connection like this one, right? Because you'll be confused. Okay, if it's like this, which one do I choose? Do I say this is 2 volts or 1,5? No, they won't give you something like that, right? But with a series connection, they can give you something like that, right? With a series connection, they can give you something like that. they can give you true volts, and the other cell being 4 volts. So the total here, the EMF here, is going to be, the EMF is going to be 6 volts, right? The EMF here is going to be 6 volts. Are we clear? We add the true in a series connection. In a parallel, we keep the one of the one cell. Are we clear? Okay. If we have got cells, remember, do you understand? Do you all understand the difference between a cell and a battery?
Yes. Yes.
That is where we should start. You understand the difference between a cell and a battery. So the current voltage inside the battery, we call it EMF, right? The total, so the EMF, the definition that I'm used to for EMF is the maximum potential difference supplied by the battery, right? That is also a valid definition, right, for EMF. More especially, they do ask it even in grade 11 and 12. What is EMF? EMF is the maximum potential difference supplied by the battery, right? And then there's another definition for grade 10s. They gave me their definitions and they are fine for their grade, right? But when you go to grade 11 and 12, the definition is the maximum potential difference supplied by the battery is EMF, right? So is this one that we use this E, or they will just say EMF, right? So this is the same thing, right? Okay, so if you are to calculate the EMF of the cells connected in parallel, right? So you don't add them. The total is going to be 1,5 volts because they are in parallel. But if they are in series, the total, we add all the voltage of all the cells. Are we clear?
Yes.
Yes, sir.
Yes, that is what I was saying. If they are in series, we add the potential difference of each cell, and then we get our EMF, or the maximum potential difference of the battery. Remember, make sure that you understood what difference between cells and batteries, because when we go forward, I'll be just saying batteries, right? But this one is just a knowledge that you need to know, because they might try to trick you. Remember what like I told you, Rin, I don't remember if you are the ones I told you. I told you, Rin, sometimes we say some questions are difficult because we have never came across them when we were practicing in the previous questions, right? And then at the end of the day, those questions are not difficult. They are just unusual. That is what they do in physical science and mathematics. Every question that you think is difficult is because it's unusual, right? So they might give you, obviously, in most question papers, they give you cells connected in parallel, you're in series, right? But if they bring cells connected in series, you should be able to apply what I'm telling you now, right? But this is what they usually bring, right? But this knowledge, you are not supposed to ignore it because you have never came across it in the past question, right? They might bring it, they've got 100% rights to do that, right? So you make sure that you understand parallel and series connection of the cells, right? So now let's go to talk about resistance, right? So resistors connected in parallel. So here is my resistor, is my R1. So here is my R2. R2, they are connected in parallel, right? They are connected in parallel. So these ones, if we are to add their resistance, that's the first thing. If we are to add their resistance, it's going to be R1 plus, going to be R parallel, 1 over R parallel is equals to 1 over R1 plus, so not plus there, what am I doing? Okay, plus 1 over R2, right? So that is how you add the series, the parallel connection of resistors, right? So if they are in series, so that one is parallel, right? They are in series, the one. So this is R1, resistor 1, this is resistor 2, right? So resistor in series, if we add them, it's going to be R1 plus R2. Are we clear? That is how we add the resistance, right, of the resistors in parallel and in series. Are we clear?
Yes, sir.
Okay, that is very, very important to understand, right? So I've shown you resistance, right? So if we are to talk about the series connection, got R1 here, and then let's say we've got an ammeter. Ammeter uses to calculate the current, right? Ammeter calculate the current, right? The A2 here. Then we've got another resistor here. So we've got another A3 here. All right. So this is the parallel connection, right? Maybe I've made it too long. Just put it here. A3. All right. So here is what happens, right? So the current in this one, because we've got the tube, let's look at it as if it was water coming in this direction, right? Water was coming in this direction, and when it gets here, it finds that there is a pipe going this direction, there's a pipe going this direction, right? And then, which means that what will happen to water? Obviously, some water will go this direction and some will go this direction, right? That is our current, right? That is our current. So here it was resistance. Now we're talking about current. All right. So when the water comes here in point, obviously it's going to divide. Some water will go that direction, some will go this other direction. Right. So which means after that it's going to flow, and then it's going to flow through the resistor and then come this direction, right? This one also flow through the resistor and come out this direction, right? And then after that it's going to come back again. Remember current, what do we call resistors doesn't use current, right? Current just flow through them, right? So the current will come flow here again, and then it will join again and come back here, right? So which means what? Which means that the current here on A1, right? A1, it was A1, right? And here is A2, and then here is A3, right? It means that the current which is in A1 and the current which is in A2, they will add up to the current which is in A3. So A1 plus A2 will be equals to A3. Are we clear there?
Yes, sir.
We're good, ne? Okay. So now let's talk about resistors connected in series, right? Right, okay. Maybe I should have put ammeter here, right? A1 and then A. Okay, let's see. This is A1, this is A2, and here we've got A3, right? So with the series connection, right? With the series connection, A1 will be equals to A2 will be equals to A3, right? So the current throughout this the resistors connected in series is the same, right? The current that will pass through here is the same. Are we clear? It will only divide when we've got a parallel connection. Are we clear?
So can you please come again?
Okay. When let's look at the current as if it is the flow of water, right? And resistors doesn't use current; it can only use voltage, right? Resistors only want voltage; they don't want current. They don't care about current, right? So the current that will come in the resistor will be the same current that will leave the resistor, right? So if it was let's say if it was 1 ampere, 2 amperes, right? 2 amperes coming into this resistor, obviously the 2 amperes will leave this resistor, and it will be the same 2 amperes that will come into this resistor, right? So on resistors connected in series, the current is the same everywhere. Oh, good.
Yes, sir.
Okay. So, but here is here is the trick about current though, right? Here is the trick about current though. So look at this statement. Resistance is how much material or device opposes the flow of electric current. It limits how much current can flow for a given voltage, right? So that is a very important statement. So it means that if this one is bigger, if this resistance is bigger and then this is smaller, right? I'm not talking about values now. I'm just talking about bigger and smaller, right? This resistor is bigger. Let's say this is maybe 50 ohm, and then this is 20 ohm, right? Just that example, right? So when the current divides here, which bigger current will go? Through A, will A1 be bigger than A2? Which one will be bigger or smaller between A1 and A2? It comes from the definition of resistance, right? Yeah.
A2,
A2 will have higher current because the resistance here, the resistance is smaller, so it doesn't resist much. This one resists more the current, resist the current more than this one. So this one resists less. So obviously more current will go where there is smaller resistance. Are we clear?
Yes, sir.
Yeah. I'm listening. Somebody said, "Sir, I'm listening."
I think they said yes, sir.
Oh, okay. So that is very, very important. Those are the basics that you need to understand about Ohm's law. If you understand these basics, it will be very, very easy for you, right? We'll go to ratios later, but I need you to understand this first, right? And then when we come to voltage now, right? Voltage, when it comes here, voltage doesn't care where is the higher resistance or lower resistance. If you put a voltmeter, remember a voltmeter, you put it across the resistor, right? A voltmeter, we've got V1 here, and then we've got V2 here, right? So what will happen? What is V1 and V2? Which one will be bigger? Will V1 be bigger than V2, or V2 will be bigger than V1? Okay, maybe I haven't said this right. Okay, on a parallel connection, voltage is the same, right? On a parallel connection, voltage is the same. So in this case, V1 will be equals to V2, right? Are we clear? On
Yes, sir.
Yes, on a series connection, V1 and V2 will be the same, right? You're on a parallel connection, V1 and V2 will be the same. But if we come here, it's V1, and we remember, you can see how I'm putting the voltmeters, right? Voltmeters read straight on the resistor, right? It connects over the resistor. If you put a voltmeter like this here, and you put a voltmeter here, it will read 0 because there is no resistor, right? Voltmeter reads the voltage across the resistor on one resistor, right? Or one or many resistors, right? So we can put V1 and V2 here, and we put V3 here. You can see V3 is measuring what? It's measuring the voltage through all the resistor, right? V3 then, right? And then here I forgot to tell you about V3 also. Let's come back here. If I put V3 here, right? If I put V3 here, all right, it's calculating the voltage through all the resistors, right? So that resistor will also calculate. It's the same. You can see that it's the same, almost the same as V1, right? And it's almost the same as V2. So in this case, V1 is equals to V1 is equals to V2, which is equals to V3. In this case, right? But here, V1 and V2, they add and give us that V3, right? So in this case, going to be V1 plus V2 is equals to V3, right? So they share the resistance. These ones will share the voltage. Will share the voltage. Remember, they will have the same current because they are on a series connection, but the voltage they will have to share. So if the total voltage here was 10, this one, if this one is 3, then obviously this one will be 7, right? That is what happened with the voltage. And also with the current, if this one was 2 amperes and then this one was 7 amperes, obviously this one was going to be 9 amperes, right? So that is also very, very important, right? That is also very, very important. Are we clear?
Yes.
You have to understand this, and you have to understand this, and then you have to understand this, and you have to understand this. That is very, very important, right? And then now we come to the questions that that they bring for calculating effective resistance, right? Effective resistance, calculating the effective resistance, right? So I'm going to give you an example. I'm going to start with the basic ones, right? I'm going to start with the basic ones. So this is let's say this is 5 ohm, and then this is 7 ohm, and this is 8 ohm, right? So we've got 3 resistors, and we want to calculate the total resistance, right? When we calculate the total resistance in this one, obviously I told you for resistor in series we use this formula, right? 1 over, right? We use the 1 over, right? So for this one, it's going to be 1 over R parallel is equals to 1 over R1 plus 1 over R2 plus 1 over R3, because we've got 3 resistance. If there were 4, we're going to add them all, right? So now we come here and do 1 over R parallel is equals to 1 over R1, which is 5, right? Plus 1 over 7 plus 1 over 8. So what is the answer?
131 over 208.
131 over 280 is 1 over R parallel, right? So if you want to solve for R parallel, the best thing that I always advise to work with the fraction, you cross multiply, right? It's going to be 131 R parallel is equals to 280, right? Then you divide both sides by 131, divide by 131. So R parallel is going to be what? What is the sum of the resistance there?
2,14 ohms.
2,14. What? You said 2,14 what? You said M.
Ohms.
No, it's
Ohms, I mean.
Okay, good. Okay, so those are our resistance. You can see that it decreased. So I'm going to explain to you why it decreased, right? You shouldn't be worried when it decreases. It has to decrease. Why does it decrease? It means that, okay, the effective resistance here is going to be less. Remember, if you have got if you have got a bigger pipe coming in, right, and then you break it into 3 branches, right, and then other water will come here, some water that direction, some this direction. Obviously the water will flow easily because it have got so many directions to go through, right? So it will flow very easily, right? The resistance will be less. When the connection is in parallel, the resistance is less, right? That is why we've got the number which is very lower than all the resistance there. Is because now you give since you connect resistors in a parallel connection, it gives them what do we call, it gives the flow of charges, which is current, right? The flow of charges to move more freely, right? It allows the flow of charges to move more freely, right? So now let's go to the connection. When we've got series connection, right? Series connection. Let's see, we've got again, we've got 5 ohm, and then we've got 7 ohm, then we've got 8 ohm, right? So there we are, right? So now if you want to calculate the effective resistance in series, it's going to be Rs equals to R1 plus R2 plus R3, right? So that's how we're going to add them. So the first one is going to be 5 ohm plus 7 ohm plus 8 ohm, which gives us 20 ohm, if I'm not mistaken. Yes, it's 20, right? So you can see the resistance now is bigger because it is being resisted here and again being resisted here and again being resisted here on the same straight line, right? So that is why the resistance now is higher. Are we clear?
Yes.
Okay, so now let's go to the a bit challenging one. No, in fact, let's start with the easier one, right? Let's start with the connection with the easier one. Okay, no, firstly, let's talk about current. Talk about current. No, I will add that later. All right, I will add that later. We'll come back here. Okay, so now let's talk about this one. Talk about this one. Combination of series and parallel connection, and let's say this one is 2 ohm, this one is 3 ohm, and this one is 4 ohm, this one is 1 ohm, right? And they want us to calculate the effective resistance, the resistance of everything here, right? So you can easily see that if these two you combine them, they will be in series with these other ones, right? So the best thing to calculate this one, you will need to calculate the ones that you can combine. You combine the ones that you can combine and then calculate the total, right? So in this case, I'm going to calculate firstly these two, right? And after calculating them, I'm going to consider them as one thing, right? So it's going to be what? It's going to be 1 over R parallel is equals to 1 over 2 plus 1 over 3, right? So which is going to be what? Which is going to be 1 over R parallel is what? What is the answer? Is it 5 over 6?
5 over 6.
Okay,
Yeah.
5 over 6.
So if you cross multiply here, I know, okay. But what if when you get comfortable, you will do it as fast as I'm going to do, right? I'm not going to cross multiply. I just know that this is the inverse. I just know that R parallel is the same as 6 over 5, right? So the answer is going to be 1, 2. Is it 1, 2?
Yes.
So it's 1, 2 ohms, right? So that is the answer for these resistors connected, right? So now when I calculate R total, I know that my R total is R series, right? So it's going to be,
So,
yeah,
how did it become 6 over 5?
this one. Remember, you cross multiply.
Okay, sir. Okay.
Sharpening. Okay. So now we need to add these ones. I'm just calling them R parallel because we already calculated them, right? And then these other resistors, I'm just going to call it 3 and 4, right? You can name them anyhow, just as long as you don't make mistakes, right? So R total or R in series is going to be what? It's going to be 1, 2 plus 4 plus 1. So the answer is going to be 6, 2 ohms. So that is our resistance, 6,2 ohms. That is how we should calculate that one. Are we clear?
Yes, sir.
Okay, and then
Yes,
they will also bring some ugly circuits, right? They will also bring some ugly circuit, but you should know which ones you're going to group, right? They bring something like this. they bring something like this. They say find the effective resistance, right? They say they call it effective resistance, right? They say find effective resistance. How are we going to calculate this one? How are we going to calculate this one? You look at the link, you look at the ones that you can easily start with, right? You look at the ones that you can easily start with, and then after doing them, you combine them, you make them one thing, and then you can think, or which ones can I combine now? So easily, these ones are easily combined, right? You can easily start with those ones, right? So with those ones, I'm going to calculate them. I'm going to let me give them the green, right? So this one's going to be, they are in series, right? So it's going to be R1 plus R2. So it's going to be 2 plus 5. So the answer is going to be 7, right? And then after that, I know that this one is the same thing now, is 7 ohm, right? No, it's not 7. What did I do? Okay, okay. It's 2 plus 3, right? Which is 5. So the 5 that I was writing there, it was the answer that I was supposed to get, right? So this one is 5 ohm, right? So I know the resistance between those two, right? So I've made them one thing, right? And then looking at the wires shouldn't confuse you, right? So because this wire just joined here, right? If it had joined here, you were easily going to see this and that are in parallel. But the way I joined it here, it was a bit confusing, and it was just there to confuse you. So you should be able to understand this wire, where can I put this one, right? You should be able to understand, where can I put this wire? If it's here, it's confusing me. Where can I extend it and not make a change in my circuit? So obviously, for the wire to come through here, for a wire to come through here, or come through all the way here, is the same thing, right? It's one and the same thing. So if it was like this, and then this one here, it can also be put here, it will be easily, you can easily see your parallel connection, right? You can easily see your parallel connection. So don't be confused about the way they've connected the wires, right? So now I'm going to calculate the parallel, which is this one, right? So it's going to be 1 over R parallel is equals to 1 over R1 plus 1 over R2 plus 1 over R3. This R1, you could have even said RS, is fine. The formulas there, they won't penalize you. As long as you are adding 3 things and they're in fraction, they won't penalize you for anything, right? They won't penalize you for anything. So it's going to be 1 over R parallel is equals to 1 over 1 over 5 plus 1 over 4 plus 1 over 5 again. Yes. So what is the answer? What is the answer?
13 over 20.
1 over R parallel is the same as 13 over 20, right? So like I've told you, you need to cross multiply, right? But once you're familiar with these things, you will know that even if you cross multiply, you're going to get 20 over 13. Yeah, R parallel is going to be 20 over 13. So what is 20 over 13? Is 1 comma what?
54.
54 ohms, right? So now we are done with this part. Yeah.
Can I ask, why are we adding the third resistance there?
This one.
Where is it coming from?
Which one? Okay, let me. Which one? This one.
No, Angry, you were calculating for the parallel, and I only see 2 into.
Okay,
There are only 2 so why?
Yeah. Okay, I told you. What about these two?
Oh.
We combined them and got them as 5. Are we clear?
And then you added them.
Yes, they are now in parallel. Remember, once you combine something, you make it one thing, then you can work it as one thing, right? So you look at the things that you can put and make them one thing, and then it will be easier for you to add the others.
Okay.
So this one was clear for me to add them because they are just in series, just next to each other. I could easily add them. right? So now, since I found the total resistance in this one, what is the total resistance in all these other ones is 1,54, right? So the total resistance for these all is 1,54. So now is this one is in series with this one, right? So my total resistance is going to be what? Let's say R total or R series, right? It's going to be the R parallel that I just got plus this other resistor, which is, I can call it number 5, right? Yes, I can call it anyhow, right? But as long as when I substitute, I do the right thing, right? So the total resistance is going to be 1,54 plus 6 ohm. So the answer is 7,54 ohm. So that is the total resistance of this circuit. Are we clear?
Yes, sir.
Yes, sir.
Okay, that is very, very important for you to understand, right? So now let's talk about, okay, let's come back here. Let's come back here. So let's say we've got an ammeter here, and then we've got ammeter 1 here, and then ammeter 2, and then ammeter 3, right? So what do we know? We know that this is the total resistance, because this one, it will be the combination. Remember, the current will come in here and it will do what? It will divide when it gets here, but when it comes here, it will gather again and combine, right? And come and pass through this A, right? All clear? Huh?
Yes, sir.
Okay. So assume that A is equals to 3, let's say let's use bigger number here. Let's use 6. Let's say A is equal to 6 amperes, right? Assume that the current here is 6 amperes. Can you find what will be A3, A2, and A1? Can you find it? Because remember, you should know that at the end of the day, A1 plus A2 plus A3 should give us 6. Can you find the current that will pass through this one? That will come.
Yes.
How are we going to do that?
Divide by 3.
Divide by 3. Nope, it won't divide by 3. Like, remember when we talked here, the bigger current will come through. The bigger current will come through smaller resistor. The smaller current will go through bigger resistor. So it won't be the same everywhere. It would have been the same if it was 5 ohm, 5 ohm, 5 ohm. It was if the resistance here was all the same, was easily going to divide by 3, it was going to be fine. But this time, the resistance, the current that will pass through here, it won't be the same as the one that will pass here, and it won't be the same for the one that will pass here. For the one reason, the reason will be the higher current will go to the lower resistance. Lower current will go to the higher resistance. Are we clear?
Yes.
Yes, so that is what is supposed to happen. So how are we go? But we know that it should be 6 amperes. The total it should be, when we add them, should be 6 amperes. Right? So how are we going to find out which one will go pass through that point? Yeah?
I think we must first find the potential difference,
We are
because
not yet. We are not yet there. There will be questions like this one, and if you go in with that thought of saying I need to find the potential difference. Nope. Sometimes you won't, because sometimes they will end up putting a voltage here, a voltmeter here, and they ask you to find the V1, the voltage here. They ask you to find the voltage. The next question, I'll ask you to find the voltage. So we don't have voltage here, so we cannot use Ohm's law. I don't want us to use Ohm's law today. For now, we'll use Ohm's law at the end. I need us to understand the ratios, how the current moves. Right? Are we clear?
Yes, sir.
Yes.
Because there will be questions like that, and they will come with a lot of marks. And then the reason why a lot of learners come out of the examination complaining, right, when this kind of question comes, is because they skipped grade 10 and 11, more especially grade 10, where in grade 10 we talk more about ratios. But in grade 11 and 12, yes, we will be talking about Ohm's law, but this kind of question will come, and will come with a lot of marks. like if they say find A3 or A2, they will ask you, they will give you around 4 marks, right? And remember, there's no formula for Ohm's law here. We are not going to use Ohm's law because we don't have the potential difference. Right? So what we do, we make ratios, right? We make ratios. Like for the very beginning, the easiest ratio that I'm going to give you is when you've got these two resistors. When you've got these two resistors, it will be easy for you to understand, right? Let's say this one is okay. We've got okay. Let me do this. Okay.
Yeah,
sorry for that. Right. Okay. We've got A1, and then we've got A2, and then we've got A3. Right. So we've got those three resistance, right? Those 3 amperes, right? Ammeters. So those are the ammeters. So let's say I3. Okay. Let's say R1 is equals to 4 ohms, right? And then this one is equals to 2 ohms, right? So what you should know about the current here, before I write the current, right? I want you to understand this. It means that because this one is half than this one, right? It means that the current that will pass through here will be 2 times bigger than the current that will pass through there, because the resistance here is 2 times bigger than this resistance here. I will clear that. Okay, because this resistance here, or this resistor here on top here, this resistor is 2 times bigger than the resistor on the bottom, right? It means that the current that will pass through here, remember, higher current, lower resistance. The current that will pass through here will be 2 times bigger than the current that will pass through there, right? So, which means that A1, A1, let's say, okay, A2, yes, A1 will be 2 times bigger than, yes, it will be 2 times smaller, yes, A2, all right? A1 will be 2, A2 will be 2 times bigger than A1. Are we clear? If, okay, like for example, if we've got 3 amperes here, it means that 3, if 2 goes here, no, 2 cannot go there because it's a higher resistance. 1 ampere will go through there, and then 2 amperes will go through there. Are we clear?
Yes.
Sure, eh? Because now we need to do this one. This one is more challenging because this one is easy because you can see that, okay, it's 3 amperes, and here it means that the current will be 2 times bigger than that other one. And when we add them, they have to give us this 3, right? So we go back to ratios. Do you remember ratio and rates? We did that. You did that in grade. Okay, you did that in grade 8 and 9, but also in what do we call this chapter? Not counting principle, but the one that comes with counting principle. It's called statistic, not probability. Yes, you will also do ratios in probability, right? You also do them in probability in mathematics grade 11 and 12, right? But now the last time you did ratios, really ratios, it is supposed to be in grade 9, right? So you are supposed to understand the ratios to divide these 6. Are we clear?
Yes.
Okay. So the ratios here is going to be something okay, usually, but the one that they bring is this one, right? Is the first one. The kind of the one that they bring is this one, right? It's this one. They like to bring this one that has got no, that one doesn't have a lot to do, right? This one doesn't have a lot to do, right? But this one have got a lot to do because the current that will go here and the current that will go here and the current that will go here will be different, right? So what you need to understand is to make ratios. What is the total for this one, for the resistance here, when you add them? Remember, I'm not talking about R total. I'm just talking about the resistance of each resistor. We've got 5 plus 7 plus 8, which is 15, right? So the total resistance there is 15, right? So you're going to say 5 over 15 multiplied by 6, and then 7 over 15 multiplied by 6, and then the other one will be 8 over 15. Sorry, 8 over 15 multiplied by 6. So what will be the answer here? Can someone give me the answer there?
2.
2. Okay, yeah.
Simplified is 2,8.
0.28, right? Okay, and
No.
then here.
2,8.
Sir.
So it's 2.8. Okay, what?
Yes.
Okay. 2.8.
Sir.
Yeah.
Why is it 15?
Oh, it was 20. It was 20. Sorry. My bad. It was supposed to be 20 because we calculated 20 there, right? We calculated 20 there. Yes, it was supposed to be 5 over 20. Yes, what is 5 over 20 multiplied by 6?
1,5.
1,5. And then 7 over 20 multiplied by 6.
2,1.
0.1.
2,1.
Oh, 2,1. 2,1. And then the other one's going to be what? The other one's going to be 8 over 20 multiplied by 6.
2,4.
2,4.
Yes.
Okay. Yes. What is the sum of this when we add them? It's going to be 6 amperes, right? Oh, clear.
Yes.
Okay, so this one is the current that will pass somewhere, and this one will pass somewhere, and this one will pass somewhere, right? So now it's time for you to decide which one will be 8.1, which one will be 8.2, which one will be 8.3. Remember, higher current, higher lower resistance, right? So the highest is 2,4, which means 2,4 will pass through here. 2,4 amperes will pass through there, and then the lowest will pass through here. The lowest is 1,5. So 1,5 amperes will pass through here, and then in the middle to be 2,1. So 2,1 will pass through here. So that is how you should find your current using ratios, right? Remember, they will bring questions that will definitely require you to use ratios, right? They will bring questions that will definitely require you to use ratios. So you should be able to. So for this one, we could have used this method, but this one was easy because it was just 3. I know that 3, if the other one is bigger, that is 2 times bigger than the other, it has to be 1 and 2. 1 plus 2 is 3, right? So we could have used the same thing. 4 plus 2 was going to be 6, right? 4 plus this 2 was going to be 6, right? So we are going to have 4 over 6 multiplied by 3, which was going to be what? Which was going to be 2. And then 2 over 6 multiplied by 2, which is going to be 1. And now we know that it's going to be 1 ampere and 2 ampere. Now it's the time to decide which one will go where. Obviously, lower current, higher resistance. Higher resistance, higher lower current. All clear?
Yes.
Okay. Yes. Now, basically, this is the very basic things that I needed you to understand. If you understand this, you will find electricity very exciting, right? If you understand your ratios, you will find electric circuits very, very exciting, right? So let me go to the notes that I had prepared. Okay. Okay, this is the where is it? Okay, it's going there. Put it here. Okay. So what I needed you to understand is that yes, I need you to understand that current in series connection. Current in series connection, okay? Key concept, in a series circuit, the current is the same through all resistance. This is what I've told you here, that current is the same here. Current is the same everywhere. Where did I put it? Yes, A1 plus A2 plus A3 is the same when we've got series connection, right? Current is the same. This is because there is only one path. It cannot pass through the other way. It needs only to pass through the same path, right? There is no escape. It has to pass through this resistor, and after passing here, it has to pass through this resistor. There is no other way. That is why it is the same, right? And then they're saying this is because there is only one path for the current to flow, right? And then we'll go to the example. They're saying if I is equals to 2 amperes in one part of the circuit, then I is 2 amperes where everywhere in the circuit if it is connected in series, right? If it is connected in series. So that is what I needed you to understand. So let's go to the next slide. Let's go to the next slide. What is the next slide? The next slide should be this one. Hope it's not this one. Not that one. It should be this one. Yes. The next slide is this one. So in the next slide, the series circuit is a potential difference dividers. Series circuit is a potential different dividers. So I told you here in series, this total voltage here is the same as V1 plus V2. They divide potential different. If they are connected in series, they divide potential different, and then they've got the same current, right? Series connection, same current, different potential different, or voltage. They divide voltage, but same current. That is the basic that I want you to understand, right? And then they're saying the total potential difference voltage is shared between the resistors in a series circuit. The sum of the voltage across each resistor equals the total voltage supplied by the battery, right? The total potential difference or voltage is shared between the resistors in a series circuit. The sum of the voltages across each resistor equals to the total voltage supplied by the battery, right? And then the formula, we've got V total is equals to V1 plus V2 plus V3, right? Like I've shown you that V3 was V1 plus V2 because they are sharing the voltage, right? They are sharing the voltage, okay? And then they're saying example, if 9 volts battery, if 9 volts battery did what? If a 9 volts battery is connected to 2 resistors in a series, when the voltage across and the voltage across one resistor is 3 volts, then the voltage across the second resistor will be 6 volts. This is what you need to understand also. You don't only need to apply Ohm's law everywhere, right? You also need to apply this, what I'm telling you now. Or if you already know that, okay, so I've got as battery here supplying let's say EMF is equals to 10 volts, and then we've got and then we've got resistors. Okay, let me put them normally. We've got two resistors here, and we know that here we've got 5 volts, right? Now let me use 5 is too obvious. Here, let's say here we've got 4 volts. With the calculator, you know that here we've got 4 volts on this resistor, right? Obviously, okay, let me put it formally, right? Let me just write V1 and then V2, right? The way they do it, right? And then they say V1 is equals to 4 volts, and they say calculate V2. Say calculate V2. You don't need to use Ohm's law everywhere, right? So because you have got V1, now you need V2. It means that you know that the potential difference that was supplied by the battery, it was 10 volts. Obviously, V2 will be 10, right? You will be 6 because it will be 6 volts because the total voltage has to be 10 volts. Are we clear? Are we clear?
Yes, sir.
That is what
Yes.
also
Yes, sir.
sharp. That is also what you need to apply on the electric circuits. All right. That is also what you need to apply on the electric circuits. Okay, and then let's go to the next one. Hope this will be the next one. Nope, it's not the next one. Just that I prepared this lesson long ago. I had to delete a lot of pictures so that I will be easily total resistance. Okay, yes. Here is number 4. They're saying calculating total resistance in a circuit series, right? Calculating total resistance in a series circuit. I've shown you this one. This one I'm not gonna say it again, right? You know, if there's the resistors are connected in series, you just add them straight, right? And then if they are connected in parallel, you use 1 over, right? So that is just straightforward as it is, right? That is straightforward as it is. And then potential different across parallel resistors. Yes, here it is. Potential different across parallel circuit, right? So potential different across parallel circuit. If we've got this one, sorry, if we've got this one, if I've got this one, these two are connected in parallel, right? And then they're saying potential different. So if this one is 20 volts, it's 20 volts. If this battery is 20 volts, the EMF of the battery is 20 volts. It will mean what? It will mean that the 20 volts will come through, and then here we've got V1, then here we've got V2, right? So what does that mean? It means that V1 is equals to 20 volts. V1 is equals to V2. That's the first thing that you need to understand. Potential difference across resistors connected in parallel is the same. In a parallel circuit, the potential difference voltage is the same across all resistors. So V1 will be 20 volts and then V2 will be 20 volts. They don't share, they don't do anything. Just go through as it is. Voltage on a parallel connection. Right? You just go there as it is. Are we clear?
Yes, sir.
Yes, sir.
Okay, so that is what you should know. Okay, and they say each resistor receives the full voltage of the battery, and then if 12 volts battery is connected across the parallel resistors, then each resistor will receive 12 volts, like the way I've shown you here, right? It is very, very important to understand everything the way I'm telling you, right? It is very, very important to understand it the way I am telling you. I'm sure even your teachers will be amazed when you answer this kind of questions, right? When you answer the circuit, right? They will be amazed. They will be impressed, right? Okay, and then we've got parallel. Okay, yes. Parallel circuit as a current divider, right? Parallel circuit as a current divider. In a parallel circuit, the total current is divided between the different branches. The sum of the branch current equals to the total current supplied by the battery, right? And then formula, we know that I total is equals to this and this, right? Like for example, if we've got a battery here, and here is our circuit, we're talking about parallel, right? Parallel. Okay, I should have put another voltage here, ammeter here. So this is A1, this is your A2, and then this is your A3, right? So they are saying that I total, I3 is our I total because it's the current that is passing through, that is going straight to the battery, right? It's the current that is going straight to the battery, right? So what you need to understand is that A1 plus A2 is equals to I total, right? So I1 plus I2, so I1 plus I2, which is A1 plus A2, right? I1 plus I2 plus I2 will be equals to I total or I3, right? I total or I3. So if this one is 2 amperes and this one is 4 amperes, then here will be what? Automatically, here will be 6 amperes, right? So it will mean that it's going to be 2 plus 4, which is equals to 6 amperes, right? So that is what we did here. Also shown you here, right, that the current will divide, but when we add it again, it should give us the total current, right? So that is very, very important also. That is very, very important also. Okay, let's go to the next slide. Taking too long locating the slides, right? Okay, I think this is the correct one. Yes, number 7 should be the correct one. Okay, calculating the total resistance in a parallel connection. I've shown you this, right? I'm not gonna do it again, right? I've shown you this so many times, I'm not gonna do it again. What did I do now? Now I don't know where to go back. Okay, sharp. Okay. Okay, so now let's go to the summary, right? Here is the summary table for parallel vs series vs parallel circuit, right? Current same through all resistors when they are connected in series, and then divide among branches when they are connected in parallel, and then voltage divide among series, and then same across all series, right? Same across. Okay, let's voltage divide across series. Yes, voltage divide on a series, and then the same across all resistors in parallel, right? And then calculating the resistor with a parallel connection, you use 1/, with a series connection, just add them as they are, right? So that is the summary. And then okay, exam type style. Okay, nope, this one's basically straight for grade 10s, right? This one is basically for grade 10. This kind of question are basically for grade 10, right? But I'm going to do the ones that should also apply in all of us, right? If I've got a battery here, then obviously they will talk about a switch, right? Once switch is closed and open, it's very important, right? It's very important to understand when switch is closed and open. Okay, so if I've got something like this, should have put the resistance here. So this is the kind of questions that they are going to ask you, right? This is the kind of questions that they are going to ask you. Let me put the A. I've made too big, right? I've made it too big. Let me use 3 ohm. Right? And then let's say we've got what? Yeah, let's say we've got the current somewhere here. Yes, let's say we've got the current through here. Okay, in fact, okay, let's firstly do calculations firstly, and then we'll bring in other questions first, right? So the first question, they ask us to find R total or the effective resistance of this circuit. Where do you think we should start? Let me name this R1, R2, R3, R4, R5, R6, R7. Yes, where do you think we should start calculating this resistance?
R3. R2
What?
and R3. At R2 and R3.
100%. It is that these ones are in series. We can easily work with them, right? We can easily work with these two. They are in series, right? So it's going to be, they are in series, right? So you can just write R, or you can say RS is equals to R2 plus R3, which is going to be 1 plus 1, which is going to be 2 ohm. So this one, we know that here we've got our 2 ohm, right? And then the next one, which other ones should we work with? Oh, what's that? Okay, guys. You should be
Okay.
familiar with this, right? The other one that we should work with is these two. These two also is just the wiring. They just put the wire in a confusing way, but these two, they are in series. They are on the same straight line, right? They are in series. This is the same straight line. It's just that there is a corner which doesn't change our connection, right? So these R1 and R6, they are also in series, right? So we've got R1, R series again, which is R1 plus R6, which is going to be 2 plus 2, which is going to be 4 ohm. All clear?
Yes, sir.
Okay. And then now we can see that this one here, the first one that we did, this one here, and this one, they are in parallel, right? So now we can calculate our parallel connection. So R parallel is going to be, oh, sorry, it's 1 over, right? 1 over R parallel is going to be 1 over this one, which is
4.
2 ohm, right? Which is 2 ohm plus 1 over this one also, or the 2 ohm is this one, right? So the other one was what? The other one was 4, right? So 1 over 4 plus this one, which is automatically 4, right? So 1 over 4. So what is the answer of this? 1 over 2 plus 1 over 4 plus 1 over 4?
1.
Huh? 1, right?
1.
So the total resistance there is 1. So the total resistance there is 1. The total resistance there is 1. From what? For this parallel connection is 1 ohm, right? The total deck resistance is 1 ohm for that parallel connection, right? So now since this one is one thing and we know the total is 1, now we can easily add it with this one. They are also in series because it's just that the corner here, it doesn't change anything, right? It doesn't make them any parallel. They stay series because they are not branching, right? So the total, R total, is going to be 1 plus 3 plus, I used 1, right? Yes, plus 1, which is going to be 5 ohm. So the total resistance of this circuit is 5 ohm. Are we clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So now let's say the current was 4 amperes. The current was 4 amperes. So we've got A1 here, A2 here, and A3 here, right? So we need to calculate A1, A2, A3, right? Remember, we're going to use the ratios because we cannot use the Ohm's law. We don't have the voltage, right? don't have the voltage, but we can calculate the voltage. How can we calculate the voltage? Okay, firstly, let's use the one that, let's firstly do the things that I just taught you today. Let's calculate A1, A2, and A3. So how are we going to calculate A1, A2, and A3? We are going to use ratios, right? Because the 4 amperes is going to come here, the 4 amperes is going to come here, and it's going to divide. The other is going that direction, the other this direction, and the other will go this direction, right? And then the higher current will go where there is lower resistance. So lower resistance obviously is this 2, which is on the bottom here, because on top here we've got 4 resistance, and here we've got 4 resistance. So automatically we know that A3 and A1 will be the same, because the resistance on that portions are 4 resistance. We have 4 ohms, sorry. Are we clear?
Yes, sir.
Okay.
Yes, sir.
So for me, I'm going to find the ratios, right? So the ratios, I know that this side is 2. Can use another color. This side is 2, and this side is 4, and this side also is 4, right? This side is 4, right? So it's going to be 4 plus 4 plus 4 plus 2, which is what? Which is 10, right? So to find the ratio is going to be 4 over 10, and then the other one, the 4 over 10 is 2 of them, right? So the other one is 2 over 10. So multiply by 4, multiply by 4. So what is 4 over 10 multiplied by 4? 16 over 10 is 1,6, right? It can't be 1. Yeah, is it 1,6? Yes, 1,6, yes. Okay, and then this other one is 0,8. Yes, the other one is 0,8, right? So which means that the ratios that I know is that, because the ones that I've got 4 is 2 of them, right? So I don't want to do, if in fact I can do, doesn't kill anyone, right? To do another 4 over 10 multiplied by 4, which I know that is going to give me 1,6, right? So now I'm going to separate my currents, because these ones are current, right? Are current. So the higher current, lower resistance. So the higher current is 1,6. Yes, the higher current is 1,6, the lower current is 0,8. So there's no need for us to talk about this other one. But the higher current will go to lower resistance. So this one, and where there is 2 ohm resistor, which means it's going to be, this one is going to be 1,6. And then the 0,8, which is the lower current, will go to this one 0,6, and also this one 0,6. So there is our currents. Is it 0,6? 0,8, sorry, it's not 0,86, it's 0,8, right? It's 0,8 is. .8. .8 and 0,8 here. So are we clear then?
Yes.
If okay, just answer me this one. If you answer me this one, I'll be satisfied, right? If we've got another ammeter there, let's call it A5. What will be the reading of A5?
It will be 4.
It will be 4, right? Because this 4 here, it just branched here, but when it came out here, it remained 4 again, right? And it will pass through this circuit and pass through this resistor S4, and then come back to the battery S4, right? So there it is. That is what I wanted you to understand today, working with circuits, more especially without applying Ohm's law, all right? Although we're going to apply Ohm's law, but firstly, if you understand the ratios, then it will be very, very easy for you to answer the questions, right? So I'm stopping it here. All right, I'm stopping it here. I'm going to send you the notes on the group. I'm going to send the notes on the groups.
Sir, how do we find the recorded classes?
The recorded classes, I have to make means. I think because I'm using my student email, you know? So I think the students from the school that I'm registered on are the only ones that I can access this. So I think I will make a plan for you. Maybe I will open the recording and just put my phone aside and screen record it again, and then post it somewhere, right? Because that one I don't think you can open it. I don't think so.
Okay.
Yes, I thought maybe it was gonna be easy, but I realized, well, no, it doesn't. I think it doesn't work. So I recorded this class, so I'll find a way to get it to you, right? So the grade 12s we needed to do the grade 11 and 12 we needed to do Euclidean, but let's put it for tomorrow, right? I think I'm tired, in fact. I don't want to force many things in a day, right? So let's do our Euclidean geometry tomorrow. Grade 11 and 12, right? We'll start at 7. Start at 7, grade 11 and 12. So let's call it a day sharp now.
Sorry, sir.
Yeah.
When are you going to do the internal resistance? And
The internal resistance we'll do it later. This one I just put you along so that you understand the basics. When we go and do our internal resistance and everything, you will be in a right position, right?
okay, sir.
You will do the internal resistance once we are doing the what do we call the Ohm's law, right? We'll do the Ohm's law, then we can do the internal resistance. Okay, sharp, no? Saying something.